Hello everyone, this is Zirui Wang, an incoming master's student from UIUC. I'm glad to have this opportunity to work with Professor Katya Sikara on multi-agent action anticipation. And today I want to present our work, the HMemFormer, hierarchical memory-aware transformer for multi-agent action anticipation. In computer vision, action anticipation attempts at forecasting future states of agents from history information. They're one of the crucial focus in AI systems that involves multi-agent interactions. This task is pivotal in numerous applications, such as autonomous driving, collaborative robotics, and home automations, because the ability to predict future actions of agents in an interactive environment can significantly enhance safety, efficiency, and job coordination. On the other hand, multi-agent has its unique challenges compared to single-agent scenarios. For example, the two agents here are asked to make watermelon juice collaboratively. Given that the agent one is trying to get the watermelon from the fridge, and agent two is preparing the juicer, what will be the action of the agent one going to be? While significant effort has been made to anticipate future actions of a single agent, prior literature largely missed the imperative components of the real-world human activities, which is interactions. So we want to model we want models to capture not only the individual action patterns, but also the intricate dynamics of interaction. So to bridge the gap with human forecasting ability, in this work, we present hierarchical memory-aware transformer, or HMemFormer, a transformer-based approach that simultaneously learns feature from both global and agent-specific memory feature. And we carry out exhaustive experiments on the multi-agent action anticipation dataset, LEMMA, to demonstrate the effectiveness of our model. This is the overall framework of HMemFormer. The motivation of our model comes from the intuition that agents' unique short-term memory provide useful information about ongoing actions, while the global memory across all agents provides shared contextual and relational information. To improve training efficiency, we use fine-tuned slow-fast network to extract action features and use these features as the input to our HMemFormer architecture. Inside our model, the global memory encoder aims to encode the long-term memory of all agents into a global latent representation that provides useful relation and contextual features. To do so, we first construct the global memory by concatenating all agents' long-term memory features to form a joint action features which is to the left on the picture. Then, by applying a max pooling with a linear projection layer, we get the global memory embeddings, which is marked in yellow. These embeddings are sent into transformer encoders that run through multiple self-attention layers to acquire to get the global memory queries. Then the local memory decoder takes in the global memory queries from the encoder and agent-specific short-term memories as the input and perform cross-attention to learn the final action embeddings. Finally, these output embeddings from the last decoder layer is used to predict future actions. The predicted actions is compared with the ground truth future actions and learned by the binary cross entropy loss as the training objectives. Here we present our results on the LEMMA dataset, which is a multi-agent dataset that includes more than 850 compositional atomic actions from 324 activities with 445 egocentric videos. For the action anticipation test, we follow the prior work and validate our model on 4 different scenarios, which are single agent, single task, single agent, multitask, multi-agent, single task, and multi-agent, multitask. We evaluate all 4 scenarios using the average precision, average recall, and average F1 score as the metric. The major experiment results is shown in the first table on top. Baseline 1 used the feature from the fine-tuned slow-fast network and perform action anticipation using a mere multi-layer perceptron for action anticipation. The baseline 2 is built on top of baseline 1 by replacing the prediction network with a transformer decoder. And this transformer decoder is composed with multiple multi-head self-attention layers. And clearly we can see that our model outperforms all baselines. We also analyze the effect of different lenses of local memory in the multi-agent context. In particular, we set the short-term memory size to 0, 5, and 10 samples with no global shared memory across agents. This table 2 shows that the HMemFormer is beneficial from longer memory size, especially applied to the multi-agent scenarios, acquiring around 2% improvement on F1 scores. We also evaluate the effectiveness of global memory. We set the short-term memory size to 10 samples and choose the local memory size from a global memory size from 0, 16, 32, and 64 as shown in the table 3. Out of the 4 choices, the model performs the best when the memory size is 64. Through all these experiments, we managed to prove the effectiveness of our design choice in the HMemFormer. Finally, in conclusion, we present hierarchical memory-aware transformer, a transformer-based architecture that uses both the global and local memory with attention mechanisms for online action anticipation. This is useful to overcome the weaknesses of the existing models that can only compute temporal dependencies or can only model agent interaction dependencies without considering both. Through experiment on 4 different scenarios involving multi-agent interactions, we show our model's capability of modeling not only the temporal dependencies, but also the interaction between agents, demonstrating that both long-term historical memory and short-term agent-specific memory are both important. In the long term, we want to further validate our model on larger benchmarks and develop a dynamic selection mechanisms to select the historical information. We believe that this dynamic selection system will capture more related information from the history. Finally, I would like to express special thanks to Xinran Zhao, Dr. Yaqi Xie, and Professor Katya Sakara for their support on the project. Also, thanks to Rachel and Professor John Dillon for making the RISC program possible, and also the members of the R Labs for their continuous support and guidance. Besides, I also want to express my thankfulness to the Army Research Lab and all other sponsors for funding this research project. I really appreciate the opportunity. Thank you for listening.